Hey guys, today in office hours, one of your classmates came and I went through these notes with them, and they at the end said it was very helpful and their questions were answered. These are my notes that I deliver in class, and so I'm going to go through them with you, and then I have a few other tabs up that we'll go into also. So here's where we start. We're starting by looking at parametrized surfaces and surface integrals. But the thing is, they're two different objects. Parametrized surfaces are one thing, and surface integrals are the other thing. The parametrized surfaces definitely lead to surface integrals, and so we need to start there. And so a parametrized surface looks like this. And this is nothing different than when we say C of t equals x of t, y of t, and parameterize a curve. That is a parameterization of a curve, like this line that I've drawn here. And so it only needs one variable in to get the point out. In this case, we have a patch in the xy plane, and there's some surface above it, and we're going to map that. So we're going to map this patch. So the u and the v come as points out of this domain in the xy plane. It doesn't always have to be the xy plane. But notice you put 2 points in, and since this is a function of 2 points, this is a function of 2 points, and that's a function of 2 points, when you put a u and a v in, you'll get 3 separate coordinates. So you will take something on the floor, and you'll map it up to a point on that surface. So u and v are called parameters, just like in the C of t, t was called the parameter. And D is the domain for U and V. That's what I said. On the floor, that is usually that fancy D. And it's called the parameter domain. That's where these two values are pulled from. So here I said it's like the old days when we parameterized different curves. So the rest of this first page is only about parametrizing different surfaces that we already know about. So in this, we're just parametrizing a cone. Now that cone has a very specific equation to it, and so we want to go inside of x squared plus y squared is less than or equal to 1. I'll tell you what that means in just a second. And so here's what we would do. If I look at this equation, x squared plus y squared equals r squared, that's a circle. And so it looks like whatever the height is, all I have is a circle of radius that height. So if z was equal to 2, this would be 2 squared, or 4, and that would be a circle whose radius is 2. And so if z was 2, the radius is 2. Now if z is 3, 3 squared is 9, so you'd have a 9 there. And then that, with a 9, is a circle of radius 3. So if z is 3, r is 3 also. So once I notice that, then what is the parameterization for a circle? It's r cosine theta, r sine theta. Well, in this case, I'm going to let u play the role of my r, and I'm going to let v play the role of my theta. And what that does is it takes it from needing 3 variables to just needing 2 for that circle. So I've encoded the radius, and as v rotates, the point on the circle travels around and around. Now, since u is the radius and z is playing the role of my radius, then here's my parameterization. So notice in the first slot here, that's just a circle of radius u. But that circle of radius u happens at a height of u. And so this works as the parameterization for it. And then, now what we have is, since we wanted x squared plus y squared less than or equal to 1, well, if we had that, then where it equals 1 is in this, just a circle of radius 1. But since a cone goes above and below the xy plane, you actually will have kind of this hourglass shaped feature. So that's what's drawn here for that. And that's why the u goes from -1 to 1, because to really keep that circle legit, you can have circles down here, because when z is -2, -2 squared is 4, and so the radius would be 2 still. So even at these negative values, you'll still get circles that are within radius 1. And then because we're going to go all the way around the circle, and my v is playing the role of theta, then I'm going to let v run from 0 to 2 pi. The next ones get a little bit easier, but that one is just sort of the way of thinking about it is what you're trying to look at there. In a cylinder of radius r, so a cylinder, it's just constant, so we can use cylindrical coordinates. And in cylindrical coordinates, remember, x was r cosine theta. Well, that is right there. Y was r sine theta, and that is right there. And z was z in that case. And so there is, there's that piece right there. Now, notice in here, it looks like there's 3 variables. There's r, theta, and z, and it's supposed to just be 2. Nope. The radius r is fixed, and so this would be a 4 and a 4, and then we would be on a cylinder whose radius is 4. So that r is fixed for each cylinder, but it kind of is a variable for this to work for all cylinders. And then because the cylinder has no top and no bottom to it, z can go from -infinity to infinity, and theta, since we're going to run around wherever we are on that cylinder, theta gets to run the whole gamut. Sphere shouldn't be a surprise. Isn't that x for spherical coordinates, y for spherical coordinates, and z for spherical coordinates? Notice again, it looks like we've got r, theta, and phi, but the r would be fixed because we're on a sphere of radius r. The radius doesn't change for the sphere that you're on. If that happens, you're not on a sphere. You're on like a peanut or something. So this is nothing more than spherical coordinates, and they will parametrize a sphere. And finally, at the bottom here, just any surface. So z equals some function of xy is, just some surface in 3-dimensional space. And so for that, let x be x, let y be y, and z is f of xy. And so notice it takes 2 inputs, but I get 3 values out. And so I do go from the floor in 3 space up to some surface. And that's how that starts to work. So on the next page, all that really goes on here is I start to show you how a map like this works. And so in this case, here's what you have. You have hidden from you like a UV plane. And that's because this function takes variables u and v, so they live somewhere, and they span a plane wherever they live. So in there you might have some sort of a rectangle, and you can divide that rectangle up into a grid. And through the map, then this little grid here gets mapped into this funky looking grid over in some other space, in this space right here. So then each of these grid lines correspond to a mapped grid line over on the other side. And the vertical ones, same thing here, those follow in there. And so you can see how this gets morphed into something else. Just like if we had a theta and a phi axis there, as you mapped things here, you would be mapping them onto on a sphere. And so that is kind of cool. Now, if you take a line through a fixed point, so we fix this point, you can see it right here. There is a vertical line, u equals u naught, and a horizontal line, v equals v naught. And so then in the map, those two lines map to something, and that point maps to the intersection. Now, on this surface, there is a tangent vector in the u direction and a tangent vector in the v direction. And so now we're going to consider those tangent vectors. This is what I just said here, the tangent vector at that point P, you see P right there, in the u direction, so we're talking about a there. Well, we're going to take the partial derivative with respect to u at that point, and it'll tell us what the slope in that direction is. And as a vector, that's what it would be. Same thing in the v direction, you would get a tangent vector there. And then just like with arc length parameterizations, it's called a regular parameterization if the normal vector, which is what you get when you cross the two. Remember, when you cross two vectors, you get a vector that follows the right-hand rule, and it's perpendicular to each of the other two vectors, and its magnitude is the magnitude of u, the magnitude of v, times the sine of theta, where theta is the angle in between them. So if that normal vector is not zero, the parameterization is regular. Okay, if they have a non-zero cross product, then they span a plane. So any two vectors that you have will have a normal vector, and once you have a normal vector, you can span that plane with those, and we've done that in the beginning. So knowing that this is not zero means that there is an angle between them, because if the cross product was zero, then there's a sine of theta in there, and that can only happen if the angle is zero between them. And so then they would be pointing in the same direction, and you would only have a single vector and maybe a different length vector, but those don't necessarily span a plane. But two vectors with a non-zero cross product will have a perpendicular normal, and therefore those two vectors will span a plane. And that n is called the normal to that plane. So in this, it's just some jargon with notation. N of p is actually n of uv. That's as a vector function. A lot of times we just write it n, or n with an arrow on the top. Tu and tv of p, or you could put the u and v in there. Just t sub u, t sub v. Another thing to note is that these are not necessarily unit vectors, so they don't have to be unit vectors. And now here's where an explanation of the notes should make it get a lot simpler. So this is not a problem in its own right. This is going to be part of what we do for a surface integral, but I'm walking us up to it slowly. So here's how that works. This is a map. It takes some domain for u and v, and it maps it, and that's some surface in three-dimensional space. So we want to compute the tangent vector in the u direction, the v direction, and that normal vector when u is 2 and v is 3. And then finally we'll compute the tangent plane there. All right, well, t sub u, I need the u derivative here. That's 2u, so there's that. The u derivative here is 1, and the u derivative here is 1. If I plug in u is 2 and v is 3, well, it only matters that u is 2, and 2 times 2 is 4. So I wind up with that vector. The u being 2 will not change those two slots. So that is my t sub u vector. T sub v then, take the v derivative, it's negative 2v. Take the v derivative, it's 1. Take the v derivative, it's negative 1. Plug in 2 and 3. We only need the 3 there to wind up with this spot. Once I have those two, I can cross them, and so there's the cross product. I went through, and this is the answer, but pulling out a scalar doesn't change the length, And so I'm going to use that as the normal vector. So what do I need for a plane? Well, I need a normal vector and I need a point, right? And so the thing is, and I have the map. So I have this map here. I know the point that I am on the floor. And so I then know the point that I am in three-dimensional space. So then that's my point. I have a normal vector. And remember, a plane is the normal vector dotted with the xyz vector. That's what gives the x minus c and those types of things. Then d is on the other side, and d is that same normal vector, but you dot it with the point thought of as a vector. And so if you do that, you can follow the work down here. That's not that important. The important part is, with a parameterization, can you get the tangent in the u direction, the tangent in the v direction, and therefore the normal vector. Okay, so that's all that's going on right now. This is just a re-summary of the plane. And so now we're going to do the same thing, but we're going to do it a little bit more general. And so what I want to point out is this. Notice in this spot right here, I used actual specific vectors. Those are fixed vectors, and this is a variable vector, and that's a variable vector, because as u varies, it also varies. And so if I would have taken this and crossed them in here, I would have had a vector that worked for any u and v. And then I could put 2 and 3 in and figure out what it would be. But it might be better, instead of using that, to use that and cross those two and be able to get the normal vector for everything. In this example here, that's exactly what happens. And so it says, compute the normal in the standard parameterization of a sphere of radius r. Well, on page 1, back here, here's a sphere of radius r. So all I've done is I've pulled that definition in. And so the distance from the origin to that surface is r. So I know that E sub r, meaning put in 1 and 1 and 1 for that, that's going to be a unit radial vector. And so the t theta, I'd take the theta derivative of that, the theta derivative of that, or of this, and this. That's right there. Notice there is no theta there. That's why you get a 0. Derivative of that's going to be a negative sine theta, and there's the negative sine theta. Derivative of that's going to be a cosine theta, which is right there. The phi derivative, that'll be a cosine phi. That'll be a cosine phi, and that'll be a negative sine phi. So there's that. When we cross them, here is the t theta, and here's the t phi. When they cross them, that's what you get right there. If you work this out, there's a negative r squared and a sine phi. I can't take a sine squared out, even though it's there and there. I only have a sine right there. So I can pull out a sine and a negative r squared, and then this is that normal vector. And the thing to note is that minus on it makes it so when you are on the sphere at a point, your vector is going to point inward towards the origin. So it points towards the origin. I made this huge thing that this is needed later, and you're going to need this a lot. Even in subsequent sections in different homework, you're going to have to revert back to this and use that. If you want it to point outward, notice I just take and strip the negative off of there, and that's an outward pointing normal, meaning if you are at a point on the sphere, your normal now points out, but it's still perpendicular to whatever that tangent plane is at that point. It would be the normal vector coming off that tangent plane. That's what we computed by those two tangent vectors and that being a normal at that point. So that right here, or more specifically this, is the normal vector for any sphere of radius r. Anytime you need that, you got it now. We did it once, it's done. Okay, then over here. So in this is the explanation for a surface integral. What I want to show you more than anything is this. In the vector field notes, there was this whole deal with arc length, this whole thing about summing up, and you get this big long sum, and it came down to this right here. And what I want to point out to you is this. Notice the parameterization, C of t, only has one variable. Our integral only has one variable. Also notice that t goes from a to b, and that's there. So whatever the parameter variable is, that's what gives you the limits of integration. Next, notice whatever your scalar function is, what you did was f of the parameterization in there. So that's f of the parameterization. And then what we did is we multiplied it by the magnitude of the tangent vector. So, and there was a huge discussion, there's a video on it and all of that already. Okay, so big important things. There's a parameterization. It dictates the limits of integration. That parameterization gets put into the f, and you multiply it by a magnitude of a tangent vector. Okay, so watch this now. In here, same start as that, but we're up a dimension, so we're up one dimension. So in this case, we had a surface, and in the xy plane, we had a path that mapped up to the surface, and the line integral gave us the area of that sheet. And so there's what we have in that. There's the same there. Notice it's a double integral. Now we use this domain. What did we do over here? We did f of the parameterization. We did f of the param. What am I doing right here? That is f of the parameterization still. And so that is exactly the same. So it's similar to line integrals. Then what did we do back here? We multiplied. So we multiplied by a magnitude of a tangent vector, right? So in this case, though, we're on a surface, and we have multiple tangent vectors in all directions. It matters, but they span a plane, and that plane does have a normal vector coming off of it. So instead of, I closed it, I'm sorry. Wait, I can do this. So instead of multiplying by a magnitude of a tangent vector, we're going to multiply by a magnitude of a normal vector. This is very, very similar to exactly this here. It follows the same. It's just this was down a dimension, and to get to surface integrals, we have to go up a dimension. Now, let me show you how this works with an example, okay? So here's what we have. Our f of xyz in this case is 1. I know that's a little lame, but it does something cool, actually. It'll give us the surface area of that thing, whatever it is. And we want to do it for y equals 9 minus z squared. Well, 9 minus z squared, if this was z and this was y, it would be an upside down parabola that starts at a height of 9 and it crosses at 3 and -3. And so, but we don't have it y and z. Instead, we have it y and z. So this is how that sits if that is three-dimensional space. So this is the part that we see right there. Okay, then, and in the beginning, you guys, this was not here. So I'm trying to draw this now. So I see what that looks like. That, since that's what it is, it's just a cylinder, because notice x can be anything you want. You're like, what if x is 5? Well, it's still just that shape in when x is 5. What if x is 10? It's still that shape. And so when you line those shapes up, they start to carry and make, it looks like a gutter, just a big long trough. But that's what it would be if it was just that. So then they start restricting it. And notice this. X goes from 0 to 3 for sure. So here's 0 out, and there's 3 right there. That's the x-axis. Z goes between 0 and 3. So notice there's 0, and there's 3 right there. And that's where that parabola does touch, this sideways parabola. Well, it's a cylinder. And then the big thing is this, though. X is less than z. Well, here in the xz plane, that's the line x equals z. And so this line right here is that line right there. And that line, as it slices through, it's going to cut that piece. And so this piece here that you see, that's one face of it that's cut when we slice a plane right through there. So that's the shape that we're left with. And now we have to figure out, how do we do this? Okay, that doesn't look like a cylinder, a cone, a sphere, or anything. And so back on page 1, down at the bottom, it told you if you had any variable is a function of 2 other variables, you can let the 2 variables stay and then replace the 3rd variable with what you know it to be in terms of the other 2. So what I'm going to do in that case is, notice in this case, x can be whatever it wants, z can be whatever it wants, it's independent in here, but y depends on z, and so y is dependent on z. So this is like x, z, and g of x, z from page 1. Now once I have that, I've made it a 2-variable function in x and z. And so, and I have limits for x and z too. I know x goes 0 to 3, and I know z goes 0 to 3 also. So in that case, now I need to find those 2 tangent vectors. So take t sub x and t sub z. That's like tu and tv, or t theta and t phi. Take the x derivative here, 1, 0, 0. Take the z derivative here. It's 0, -2z, and 1. We will cross them in general. Notice this is a generic normal vector. And then I'm going to take the magnitude of it. Why? Because I need it right here. Now, what is this? That is going to be 1 no matter what g, no matter what g is. So the function is 1. So this is going to be 1 times whatever that magnitude is. So I'm figuring out the magnitude there. Square root of that squared plus that squared plus that squared. It's 1 plus 4z squared. Notice in here, so when we look, my floor now, this is the weird thing. So in everything I've done, I've shown a domain down here and something up here. This one, though, really is this. We have a domain here, and we have a surface out here, and this is being mapped up to that surface. And so I put this right here is that piece right there. That is the floor, and then this thing lives above that in space. And so I use this to encode these limits. And so notice on this, if I put x first and then z, then x goes from 0. You can't go 0 to x. It has to be 0 to z. So 0 to z. And then the smallest z is 0 and the largest z is 3. And so those are right there. Notice doing the x first just pops an x off. Notice in this, we're just going to replace that x with a z. And so it's right there. And notice that z allows us to make a u substitution. So it works out. You get that answer. That's the answer for it. But that's start to finish how you would do it. So you need the f of, you need the normal vector, you need the magnitude of the normal vector, and you need to figure out where is the floor in there so that you can encode those limits into that double integral. In the previous example, here's something that I'm going to show you, and then I'm just going to leave this here with us. If z is just a g of xy, just some surface the way that we think of surfaces, you can think of it like this or just like that. Most books just leave it like that, leave it x, y, and g of xy. Then t sub x should be 1, 0, and g sub x. And t sub y should be 0, 1, g sub y. And when you cross them, you get this. And when you take the normal vector, you get the square root of that squared plus that squared plus that squared. And so this is what you wind up with as that magnitude of the normal vector right there. And then notice that in this thing, we need f of the surface. Well, my surface is that. And so if I have f of x, y, and I saw it, it's under my hand though, I'm left-handed. So it's right there, but I use the x, y, and z out of the parametrization. So x is still x, y is still y, but z is g of xy, and that's right there. And so that is what it looks like. And the reason I'm showing you that is because here is a from some college in the United Kingdom, and here's their notes on surface integrals. And if you turn the page right here, they have the 1 plus dz dx, that's z sub x, or g sub x squared, and that's z sub y, or g sub y squared. And so notice that goes right in there, and that's the same. If you flip to this page, here they have, they're using r as for tangent in the x, tangent in the y. They cross them, and you get this. You take the magnitude of it, you get that. And so here is that function right there. And finally, in this, these were the examples I was going to do before, and you notice I drew some pictures and underlined some stuff in there. I might still upload this, but anyway, the point is in there, this last formula is nothing more than this formula using a very specific parametrization. And since any parametrization, any surface that z equals f of xy, you can do it. This will always be the normal vector, that will always be the magnitude, and that will always be the integral that you do. But there is a problem. Sometimes you can't integrate. So I'm going to stop there. You guys have the homework. It's on the parametrized surface integrals. Notice that the next thing is over vector fields. And so in vector fields, it's more like this when here's the deal. Since the magnitude of this is the square root of something squared plus something squared, you always have a square root in there. And most of the time, you can't do a scalar line integral. But in the vector, you see where those two cancel, and it happens to be that way because that is a unit vector. And if you look here, what's going to happen is right here, that canceling. And notice it's f of the parametrization. That now is a dot. And when those cancel, that's a normal vector. Notice before it was f of, that's still the parametrization. That's still a dot, as in a dot product. But this time it's a tangent vector. And what changed before for us? The tangent vector changed to a normal vector. So this is the same as vector line integrals. So if you want, you can go through that. I will make a video on this later on, but that should be enough to get you started. That is an explanation of my notes. That's every bit of detail that I can tell you about them and show you where everything came from. We didn't go through the integrations, but that's not the hard part. The hardest part, honestly, is getting those limits and parametrizing the curve. Those two things are the hardest. And that's why on this first page, there's 1, 2, 3, 4 different ways to parametrize almost anything. So use that to your advantage, all right? Take care, guys. I'll make another one soon. Bye-bye.